Hi, this is Professor Urban, and I'm getting ready to present a video clip that helps explain a paper which is published in this journal. This is the outline for it, and first that's me, and then we'll talk about each of these briefly. First, a quick video abstract for the publication, and then we'll discuss models that are applicable of the human system, of the engineering perspective on the human system, and also a mathematical model of the human system. And we're talking now about concentration of cortisol in humans. We'll go ahead and describe all of those models, and then tell about a discrete math way of solving the mathematical model directly, and then an AI method for solving for the model, which is much faster and more efficient than the numerical method. And we'll show you some examples. So let's go right away to the PowerPoint on it. And here we are. That's me. And here are the other authors. Dorin and Perogamvros are endocrinologists, and Qualls is a statistician, mathematician, statistician. And the overview of the work is that we're going to look at what happens to cortisol. So here we have a way of showing it, that the human body here, represented just by two rectangles, there's a vascular space, and then the extravascular space for our purposes. We'll insert a certain amount of cortisol into the vascular space. Some of it will diffuse into the extravascular and then later out, and then it will also clear. And the diffusion is the process between. Also, the vascular space contains cortisol that is free, and also that is bound to albumin, and also that is bound to CBG. In the extravascular space, we don't pay much more attention, other than it's not in the vascular space, and it is diffuses in and out of the vascular space. And in order to know where that cortisol is going when, we need to solve the mathematical model one way or the other. And the first way we'll show is using numerical techniques. It works, but it's hard and it requires a pretty reasonable computer. And the other method is artificial intelligence using artificial neural networks. So it has to be trained once, which is not an easy step, but then afterwards the computing is simple. And I guess I'm hiding the part that says that it solves well. So if we proceed, we see just an example, which we'll see more of later, of what happens when we do the solution. The math is coming right up, and the little black dots are the measurements. There's 15 measurements made over time in minutes, and solving and here's some known parameters and otherwise measured albumin and CBG concentration. And then we're finding these three numbers here. The one we most care about is the clearance rate, alpha. The green and other colors I'll briefly mention. Green is the concentration of cortisol adsorbed to CBG. The red is adsorbed to albumin. The maroon is not in the vascular space, that's in the extravascular volume. And the blue is the free, and that's the part that does the work. So in order to solve equations about all this, we need to have equations to start with. And so first of all, a medical model, more or less as a conceptual illustration of the system. We're primarily interested here in the cortisol part, where there's bound CBG and albumin. And right here we have tissue, so that's the extravascular, and free cortisol, which is, and you can see it entering and exiting from this rectangle. And you can see all these different arrows and everything, but and it gives a good concept, but it doesn't give you a math equation. Now the engineer approach is, already looked at this briefly, and we have vascular volume contains free CBG and albumin bound, and the extravascular is another compartment as well. So there's a total of 4 compartments, and this is the part that's going to lead to a set of mathematical equations that we can solve. Here are the equations, and to look at them just like this is not very informative. But if we pick it apart a little bit, you can see that it's very straightforward concepts underlying these equations. I've circled here the adsorption of CBG of cortisol to CBG, and this is the term here, which has to do with adsorption. So this equation has to do with CBG, and it's absorbing in proportion to how many open sites there are, times the concentration of free. And up here we have the opposite. So it's anything that adsorbs, it has to leave the free. So this first equation has to do with free, and so it's a minus sign. The minus is way over here and the plus is here. So it's just telling us that it goes from free to adsorbed, and this is a term that's required in the chemistry equation, basically. So then the other possibility is that it gets, that was adsorbing, this is desorbing, and so in desorbing, it adds to free and subtracts from CBG. So you can see the sign change, and these are the standard chemistry equations for that. And now that we do the same, basically I'll go quicker for adsorption to albumin. This is the adsorption. So when it's adsorbed, it increases the concentration of cortisol adsorbed to albumin, C sub A, and it decreases the amount in free. Here's the minus sign again. And the opposite is true for desorption. When it desorbs, it decreases the amount that's adsorbed, and it increases the amount that's free. So that's all those equations do. And the last one has to do with the difference in concentration between free and the extravascular volume times a constant factor. It's derived from Fick's first law of diffusion. And you can see that in this form, it's increasing the concentration in the extravascular. And to do that, of course, it has to leave the vascular, and it lowers the vascular free. So it's going from here to here and back. And then finally, the last two components are that in order to get the cortisol in the first place, one way is from the secretion within the body of cortisol into the vascular volume as free, from which it can do the adsorbing, desorbing, and so on. But it also clears, and always leaves the body, or leaves the is no longer active. So the equations are pretty complicated looking, but they're quite straightforward. Now, how can we solve this system of equations using numerical techniques? No problem. This is a block diagram that explains that, and I've broken it out so you can see each part a little better. The first few steps are to gather the known data, that is values of kappas and so on in the equations, and then gather the measured data from the subject, So 15 measurements across time. And then we produce an estimate of the unknowns that we're trying to find, the 3 numbers that we're trying to find. The next thing that happens is that we make a loop here, and we do some calculation, check it, see if we're finished. If not, do it again. And the stopping condition should be something like it no longer gets better, or it's accurate already, something like that. What about that particular segment? Well, it's interesting, especially because it has a numerical method embedded within another numerical method. So this one here is an integration function. It's a discrete math, digital process to find what turns out to be thousands of concentrations as a function of time, solving those differential equations. And then we compare the measured and the computed, and if they don't agree yet, then if they get a no by checking, we come up here and make another loop through, make some adjustments, and do it again, and do it again, and do it again until we get to a stopping condition, and then we're finished. We'll see that happening here in a moment. Then we save the results and call it a day. So I guess I could put myself back in. So in this case, we have a thing that looks like this when it's done its solution. And in a few minutes, I'll demonstrate this. Now, the other alternative is to solve these with AI. So in AI that we used in this case, I'll get myself out of the way, has 15 inputs, which are the measurements at these different time points, 10 minutes, 20 minutes, 30, 45, and so on. That's listed in the paper. And each of those artificial neurons on the input layer are connected to the first hidden layer, and there's 30 of them, and I can't draw them all, and each green line represents a weight, which is a number. So you take this number, multiply by that number, take it here, sum it, and then pass it along to the second hidden layer, which also has 30, and then in the output only has 3, and I just didn't use the fourth. It's not even there. In the actual simulation, it's not there. So by doing that and training that so that the weights are accurate, and you do this through a standard training called backpropagation, and that's better detailed into the paper itself. But the weights get more and more tuned so that when you apply an input, it gives a pretty close accurate answer for the output. And it doesn't have to go through those loops. It doesn't have to do the integration. It doesn't need a hefty computer to do the job. And this is just a graphical representation, which I'll show you it functioning here in a minute, of doing such a thing. I left off all the other green and magenta and red and so on, just showed the solution. And these are simulated values of measurements, so of course it gets it very accurately. And our conclusions are coming up. I want to go ahead to demonstrate the operation of these programs first. I will go to this one, and I'll move it a little so you can see which one we're talking about. Put myself back in. And this is a little application developed with MATLAB, and it's already got a solution given and some information here. So I'll just clear the plots and show you how to import. So we can import this, and this program is available in the supplementary materials, so you can download it and run it, and it'll access any of the data sets and functional things that you need from MATLAB, and it doesn't there's no charge for that from MATLAB. So I'll just pick the first one, number 1. This is a set of data sets that I've provided, but you could make your own. And then I open it up, And of course it navigates away. Being a computer, it's going to do what it wants. So it navigates away, and there we are. We've just loaded it. It doesn't say so yet, but now I go ahead and click solve, and it will solve that number 1 problem. It's running off solving. It takes a little while because the numerical approach takes some time. And there it finished, and you can see the different curves that I've already mentioned before, and it said it took 8 seconds. Now I can tell you that if you do this on a better computer, this is on a slow computer, purposely a desktop, laptop, not a desktop, and it's old, and it's just to see what's the difference, and it's about 10 times slower than a decent, better computer. So instead of 8 seconds, it would be a second or so. And there's our solutions. I could do it again for another data set if you want. We could lay them on top of each other. I'll go ahead and do import. It'll navigate me away again. I'll go to number 2. I'll go open. I don't understand why it feels it has to navigate, but it does. Then I can solve without clearing first, and you can see the 2 different data sets lying on top of each other. It takes a moment to generate, and you can see that it's done that. And anybody that's done modeling of physiological data knows that's amazing to get it this accurate. So if I clear it, I'll just be able to see, I'll solve it again, and you'll see just number 2. And it took 2.7 seconds. It's a little easier problem to solve. It didn't have to make as many loops to get to the stopping conditions. Now the faster, better way, I think better, is to do this by artificial intelligence technique, which I have also a program for. So here is the program, and I have not included all those pretty colored lines, but they could be computed easily and plotted. I just didn't do it. And so it's solving using total, same as the other, and we can put in a number here, up to 500 different trials. So we could put 456. I have no idea what's going to happen. Press return, and it solves. Well, you can see that it solves faster. It tells us it solved in 7 milliseconds. Wow, that's a lot faster than 7 seconds. So, and it doesn't require a big, heavy-duty computing device. So it could be put, once a network is trained, of course that takes some time and some effort on a better computer. But you could run this on an edge device, which would be fit in the palm of your hand and cost less, a lot less than a computer, and it can be used in a clinical setting that way. And you can see the accuracy. This could be improved by training differently. So we have 2% and -% and -0.6%. So those are probably within the accuracy of the measurements. Let's do one more just for fun. Let's do 59. I have no idea what it's going to do. I'll press return, and look how quickly it solves, this time in 3.2 milliseconds. And with the better computer, it solves even faster, maybe 10 times as fast, depending on the problem. And you can see the accuracy numbers are quite good. Fair enough. So we go back to our conclusions, and we draw the following conclusions. That we applied the AI to the four-compartment model of cortisol concentration. It worked. I just demonstrated it. And the AI method is suitable for small edge devices, which could be held in the palm of your hand and not cost very much, and could be in every patient could have one if you needed it to be dedicated. The network architecture that we used, but is not magical, is 15 input neurons, 2 layers of 30 hidden neurons, and 3 output neurons. And all of this confirms everything we did, confirms the numerical solutions as well, which I showed the program to do that also. So normal, with normal subjects and CBG deficient subjects. So with that I conclude, and I salute you.